Hey, Pre-Calculus, I've got the last part of the 3.3 notes for you. So we ended on I believe number 6. So let's get started back here. So I introduced function composition in the previous video very thoroughly. This is just a matter of practicing what we talked about. So h of x. So remember, this is h of f of x. So what we're doing is we're taking the function root x, h of x equals root x. All right? So normally it looks like this. But for function composition, wherever we see an x, we're going to put an f of x. So h of f of x is equal to root f of x. Now root f of x is going to be root 4x squared minus 4x plus 5. Which ends up being the first part of our statement. You can't simplify that any further. That's going to be h of f of x. Now, what is its domain? Well, if you've got something underneath a root, you're going to set that thing greater than or equal to 0. Because we're not dealing with non-real solutions in this. So you'd say 4x squared minus 4x plus 5 is greater than or equal to 0. There's actually two ways of analyzing this. The first is to just find critical numbers and set up your intervals like normal. So the algebraic approach is to say 4x squared minus 4x plus 5 equals 0. This is how we get our critical numbers. And if we plug this into the quadratic formula, okay, x equals 4 plus or minus the square root of negative 4 squared minus 4 times 4 times 5, you'll notice that there's a negative underneath the root, okay? There's no real solution to this. So if there's no solution to the equation in which we're trying to find the critical numbers, that means there are no critical numbers. So there's no crumbers. Which means the interval that you test is negative infinity to infinity. So it's kind of like all in. It's either everything works or nothing works. So we're just going to pick a point between negative infinity and infinity. 0 looks good. So 4 times 0 squared minus 4 times 0 plus 5, that's a positive number. Yes, works out. So our domain is negative infinity to infinity. Now there's also an algebraic or a graphing approach, sort of like a geometry thing, where if you know how to graph 4x squared minus 4x plus 5, you can just compare it to the x-axis. Where is it less than 0? Where is it greater than 0? So this is what it looks like. So we talked about how to graph parabolas in the last chapter. In fact, we talked about how to put it in vertex form. You group the first two together, take out a 4. You're left with x squared minus 1x. All right, and then the plus 5 just kind of goes off to the side. You add the perfect number, which is the middle divided by 2, half, square it, 1/4. And then we have to offset the number we created. We created a fourth of 4. We created 1. So now we have to subtract that 1 from that part. Anyway, this is just review for you guys. X minus a half squared plus 4 is what this parabola looks like in vertex form. So you would go right a half unit up 1, 2, 3, 4. And this is the vertex. If it's got a positive leading coefficient, that means it's upward. So we basically got a stretched parabola that moves upward. Where is this greater than or equal to 0? Well, it seems like it's always greater than or equal to 0. Always above y equals 0. So 4x squared minus 4x plus 5 is greater than or equal to 0 always. So I don't know, I kind of like the connection between algebra and geometry because they're two completely different ways of looking at this function, but both should make perfectly good sense as to why it's negative infinity to infinity. All right, let's check out number 7. And prepare yourselves, guys. This could be a somewhat lengthy video. The last two take a while to explain. All right, number 7 is asking you to subtract two composite functions. So just keep in mind that we're doing h of k of x here minus h of g of x here. Now k of x, if we look at our list, is going to be a polynomial. And our g of x is going to be a rational function, aka a fraction function. All right, so this is just a square root function. So it's just root 3x squared minus 3x plus 4. And this is going to be the root of x over 1 minus 2x. So it's sort of like I've got two different gotta be greater than or equal to 0 scenarios. So what you're going to do is you're going to say, I want to figure out what this is, because that'll give me its domain. And then I need to figure out what this is. It'll give me its domain, and then we merge the two together. We find the combination of the two. We find the intersection between the two. We find out what these two domains share, and then that will be the overall domain for the original function. So with this one, I kind of feel like you guys are going to go for the algebra approach more than anything. So we'll do algebra first. So critical numbers. So what crumbs do we got here? Well, we set this thing equal to 0. And unfortunately, I gave you an example where, again, it's no solution. I'm not sure exactly what I was thinking when I did that, but I think it actually makes for quicker work. So, looking at the bright side of things, there is no solution to this. We just figured out what the no solution means. It means you're going to test negative infinity to infinity. So pick a number between there, 0. If you plug it in, it's going to be positive 4 is greater than or equal to 0. A positive number means our domain for just this part is negative infinity to infinity. Over here, we kind of have to go the critical numbers approach. I guess you guys could graph that, but it seems like it would be more burdensome. So let's just do the algebra. So you've got a top critical number of x equals 0, and we put those in brackets because of the equal to right here, and it's the actual 0 of the function. When you set the bottom equal to 0, that's kind of like, usually it's going to be an asymptote, but sometimes it could be a hole in the graph. The bottom equaling 0 is going to be x equals a half. All right? Bottom equals 0 yields that solution. I'm kind of skipping some steps here so the videos aren't as long. Once we've got our two critical numbers, now we are going to have one interval that stops at 0. And remember, the infinite values always have parentheses. We're going to have another pit stop at a half. And then we're going to go all the way to infinity. Not beyond, just to infinity. And then test some points in between. Let's see, let's take a quarter. Right, and then we're plugging these into the red fraction here. So, to make quick work of it, this one ends up being negative, this one ends up being positive, and this one ends up being negative when we plug these values in and we compare it to 0. So we're looking for positive values, so that doesn't work and that doesn't work. Okay, so the domain of this part of the function is just an itty-bitty sliver. It's just from 0 to 1/2. So now, final answer for the domain. We've got our composite function. It's this. There's nothing really else to do with that monstrosity. But the domain itself is going to be the intersection of negative infinity to infinity and 0 to 1/2. By the way, here's what that looks like. The upside down union symbol is the intersection symbol. Right. And then don't just leave it like that. Then you actually compute what that intersection would be. It ends up being, what does everything share with just a little sliver? It's just a little sliver that they share. Right, because I could draw a number line and say, here's negative infinity to infinity. In red, it's everything on the number line. That's negative infinity to infinity. In blue, this is 0 to a half. They share this space right here. This is the only spot on the graph where they actually share. Okay? On to number 8. Now, number 8 looks a bit intimidating because it's a composite of 4 different functions. It's basically saying we're trying to compute the function f with g plugged in, with h plugged into that, with k plugged into that, with 1 plugged into the k value. So we close the 1, close the k, close the h, close the g. The g, wait. I don't know if we need one more. You know, it's not worth spending our time on right now. So what we do with this is we just take it one itty-bitty step at a time. K of 1. The function k of x is a polynomial. It equals 3x squared minus 3x plus 4. All this is stating is plug in the element 1 for x. You can compute that value for an actual constant value. This would give us 3 minus 3 plus 4. 4 is k of 1. So that's an important value. I'm not going to circle it. I'm just going to kind of say like, hey, that's a... Well, I guess I did circle it. I used a little scribbly circle. Anyway, got that. Now, this tells us that, hey, h... Instead of k of 1, I can do h now of 4, because 4 equals k of 1. So it's just a basic replacement of 4 now. H was the square root of x, so all we got to do is say it's the square root of 4, which is 2. So that's the next element. So we go to g now. Instead of g of h of k of 1, I figured out what h of k of 1 is. It's 2. So you're going to do g of 2. G is just that fraction function that we had, where you put 2 over 1 minus 2 times x. So it's just 2 over 1 minus 4. 2 over negative 3. It's negative 2/3. And then we go all the way out to the last one. It's going to be the function f of negative 2/3 now. F was a polynomial. 4x squared minus 4x plus 5. There's no shame in checking this on your calculator. So let's go ahead and do that. Just to be certain that everything is absolutely correct. We get 9.4 repeating, or the fraction 85/9, or the mixed number 9 and 4/9. I'm a fan of improper fractions, simplified, or mixed numbers. So my final answer is 85/9. The box means for sure that's the final answer. All right, now this is a tricky one, and I'll try to find another YouTube video in which they address this. In fact, I would just do a YouTube search of function composition ordered pairs, and I think you'll come up with something that gives a similar explanation to what I'm about to give right now. Okay, so what is this supposed to mean? Well, we know what this notation means. We know this is f of g of x. So this is just saying instead of equations representing functions, this function is 1, 2, 3, 4 ordered pairs on the xy plane. There are 4 elements to f, just as there are 4 elements to g. So what they're saying is, what happens when I input the element of g into f? Is anything going to come out of it? That's the question. So what you're doing is you're saying, for this one in particular, take every, I'll say in quotes, element of g of x, every ordered pair, and plug it into f. And I'll put that in quotes too, because it's kind of confusing what that's supposed to mean. So, if we start with g, we have to start with the x values of g. If we start with our inside function g, the x elements are the starting points. So what are the x elements of g? 4, -3, -1, 5. So this process starts with what's going on with x equals 4? What's going on with x equals 5? Sorry. What's going on with x equals 4? What's going on with x equals -3? What's going on with x equals -1? And what's going on with x equals 5? Well, here's what's going on. When I plug in x equals 4, I get -4. G of 4 equals -4. So I can do a complete replacement of g of 4 with -4. So let's do that with each of these. So you're doing f of g of -3, f of g of -1, f of g of 5. -3 gives you 2. So that g of -3 gets totally replaced with 2. The -1 gets replaced with 4. And the g of 5 gets replaced with 12. So then, f of -4. Now we go to our f function. Okay? We're inputting -4. Whatever its output is the new y element. And I'm going to have to get rid of this, guys. Sorry. I just don't have the room. So when I plug in -4 for the x's, there is no -4. There is no x equals -4 element in f. Which means our composite function has an undefined element there. If you try that again with 2, There's no 2. So that one's undefined as well. When you plug in 4, though, for the x value, you output -3. And when you plug in 12, you output -1. So, our composite function, f of g of x, has 2 elements in the set. The first element is I input -1 at the very beginning, I output -3. For my second element, I input 5 and I output -1. These undefines just basically communicate to us that those functions don't really create anything new. It's kind of like if there's a domain issue in our input function, it doesn't yield anything in the output function. So why don't you guys pause the video and try the second part on your own, and then I'll put the answers up, and that'll be all for the video. All right, you paused it. You either tried it or you're just waiting for me to show you how to do it. G of f of x. All right, so we start with the function f because f is the input function. The x values are the ones that are important to us, so x equals -5 is of consequence. X equals 14, same deal. X equals 12, and x equals 4. Okay, we are plugging that into here, so you're doing g of f of -5, g of f of 14. That's kind of an annoying voice, so I'm going to stop doing it. G of f of 12, and then g of f of 4. Now, let me double check. Yes? Okay, good. Now, f of -5 is 4. F of 14 is 8. F of 12 is -4. No, -1. And then you got -3 for f of 4. All right, now we've got inputs for our g function. So let's check it out. G of 4 is -4. G of 8, undefined. G of -1, ooh, got it, 4. G of -3 is 2. So the composite function, g of f of x, equals the element -5, -4. Not this one. The element 12, 4. And then the element 4, 2. Okay, I think that's it. Thanks for sticking around for 24 whole minutes. Appreciate it.